ML and why do we need it? So for those who were not here yesterday, ML or machine learning is teaching a machine to take decision on past experiences. Let's take an example. Let's say you want to build a model that detects if a mail is spam or not spam. So you write an algorithm, then you feed loads of data about both spam mails and not spam mails. Then computer builds a logic around that data. So if you receive any new mail, then computer put based on that logic decide whether this mail is spam or not spam. So now let's get started with day 2. 1 minute. Can you guys see my screen? Mayur, can you see my screen?
Yeah, it's visible.
Okay, then let's start with day 2. Now, there are mainly three types of machine learning: supervised, unsupervised, and reinforcement learning. Uh, so, like, before we get into all that complicated stuff, there are two things you need to understand. One is feature, and another one is label. So, feature is one column of data in your input set. Now, many of you might not have seen a data set before, so don't worry, I've got you covered. This is how a data set looks like. By the way, this one is called Irish dataset. It's a very famous dataset. It has four features: sepal length, sepal width, petal length, petal width, and it detects whether our species is like there are three labels in this dataset: Iris setosa, Iris virginica, and Iris versicolor. So this one column is called a feature, like sepal length. Then sepal width is another feature. So in this dataset we have four features. So a feature is one column of data in your input set. For instance, if you are trying to predict the type of pet someone will choose, your input might include age, home region, family income, etc. So, like feature can be anything. Like let's just take this cat for example. If I show you image of a cat, you will very easily identify it's a cat. But what did you saw on what basis did you decide it's a cat? You might have seen its ears, its tail, its fur, its nose, something like all this stuff are called features, and the label would be cat. So okay, label is a final choice such as dog, fish, iguana, rock, etc. All this. Then okay, now that we have understood features and labels, let's see what supervised learning is. Supervised learning describes a class of problem that involves using a model to learn a mapping between input example and target variable. Uh, like let's just see this data set again. We have been given this data set. We have all four features: sepal length, sepal width, petal length, petal width, and we also know that this species is a Iris setosa. Okay, so when you have been given both features and labels, then that model is called supervised learning. Supervised learning involves mainly two types of problems. One is a regression and another one is classification. So regression is a technique for investigating the relationship between independent variable of features and a dependent variable outcome. Don't worry about if you don't understand anything. You can just ask in chat. So in regression, we just find the relationship between features and labels, some mathematical relation. That's all. And in classification, we classify whether again, whether this mail is spam or not spam, whether this animal is a cat or a dog, like that. We classify it into stuffs. But in the end, we are just finding relationship between features and labels in both classification and regression. So what's actually the difference between classification and regression? Regression In regression, our model returns a numeric value, while in classification, it returns a label like spam or not spam. But in regression, it will return a numeric value 1, 2, 0, something like that. That's the main difference between classification and regression. Here's a meme for you guys, just in case you get bored anywhere in theory. If it's called machine learning, the machine should learn it, not you. Okay. Now we'll look at some models, ML models. Uh, the first one is linear regression. Linear regression analysis is used to predict the value of variable based on value of another variable. The variable you want to predict is called dependent variable. The variable you are using to predict the other variable is called independent variable. If you remember our iris dataset, so all these features are called independent variables. They don't depend on anything. But our label, that is iris setosa, it depends on all four of these features. So it's a dependent variable. So our label is a dependent variable and all features are independent variable. And now let's go on to linear regression. Mayur, can you see my paint tab?
Yeah, I
Hello?
can see. Yeah, yeah, yes.
Okay.
One more thing, like you can hide that pop-up of sharing.
Okay. So linear regression, let's say we have been given a data set that which is price of houses and area. So now area is an independent variable, it doesn't depend on anything, but price depends on area, obviously, area of house. So let's say our house was 50 meters square, its price is 50 lakhs or something. Let's keep it lakhs. Uh, if area was 60, our price is 65. For 65, 67. Okay, like this, we have been given four data points. So these black dots in this graph are our actual price. And in linear regression, we try to uh, make a best fit line. Don't worry about what is a best fit line. Let's just consider this a line for now. Don't worry much. So okay, we make a line, then we see difference between a predicted value and actual value. Let's say we made this line here, this black one. For 50 lakh, our predicted price is this yellow dot. Okay, for 60, this yellow dot. For 70, this yellow dot. So the difference between a predicted value and actual value is called error. And in linear regression, there's a loss function which is mean squared error. Now we have loss function in all models, but mean square error is only loss function for linear regression. And what is mean squared error? I hope you all guys know. We'll square all the errors, then calculate average of it. That's mean square error. So that's a loss function in linear regression. Then uh, let's say we first made this line. Okay, we got some mean square error. Let's say it was 300. Then we made another line, something like this, and we got another mean squared error, which was, let's say, 200 this time. So if you see, mean squared error or loss has decreased. So this line is better fit for this model than compared to this black line. So we keep making new lines and finding mean square error, and we keep doing this until mean square error stops decreasing or starts increasing. When we find such a line, we call it a best fit line. Then if you remember what line's equation is, it is y equal to wx plus b. Here w was slope and b was y-intercept, obviously. But in machine learning, we call this w as weight, and this b, we call it bias. And this entire equation is called score function. So we talked about two function here. One is a loss function and one is a score function. Score function is equation of a line and loss function was mean squared error. Now in different algorithms, loss function and score function will be different. It won't always be mean square error and y the equation of a straight line. Okay. But here we only had one feature, that is area. Let's say we had another feature which was number of bedrooms. Let's say this one had one bedroom, two bedroom, one bedroom. Okay, so we have one more feature. Now we obviously can't plot a line here, so score function is different here. Can anyone tell me what would our score function be? So okay, score function here is w1 x1 plus w2 x2 plus b. So if there are n number of features, score function will be w1 x1 plus w2 x2 plus w3 x3 dot 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 wn xn plus b. So that's a score function for a linear regression. And okay, I hope you understood what a linear regression is. Then difference between actual price and predicted value is called a error. Okay, but how do we decrease our loss? There's a thing called optimization. Like I just told, we keep changing our line, that is, we keep changing our weights and biases till we find the best fit line. This process is called optimization. Uh, Now, before we move ahead, there's a concept called learning rate. Learning rate or learning rule is the factor which decide how fast or slow or how accurately the artificial network can be. Like how fast or slow it's going to change. That is called a learning rate. Now, uh, there's a concept called gradient descent. Gradient descent is an iterative first order optimization algorithm used to find a local minimum or maximum of a function. If you did not understand this, don't worry. If you remember, I just told you about a loss function. So in linear regression, it was mean square error. It won't be always mean square error. It's going to be different for different algorithm. So let's say for some algorithm, our loss function of mean is y equal to x square. Okay. Now you need your loss to be minimum because obviously, who wants loss? So you want your loss function to be minimum. Then this is our loss function. In some algorithm, we don't know y equal to x square. So let's say you take some value of x, let x be 5. We are just going assuming a random value. Then y will be 25 at x equal to 5, right? Now we are trying to find x where a y is going to be minimum. Obviously, you can see a graph and say it's going to be 0, but in real world, we won't get such easy loss functions. There will be 5 to 10 features and all. So it's not really that easy to find a loss function. That's why we use something called gradient descent. Okay. So on we assumed a random value of x that which was 5 and we got y equal to 25. Now I want a new x. So I'll have to shift my old x somewhere. Then this formula here, x new equal to x old minus learning rate into slope. This is how we find a new x. Okay, so let's try to find a new x. X new is equal to x old was 5 minus learning rate. I just told you about learning rate. It's the rate at which like it's the rate with which like model works, or the speed at which it will change. It's called learning rate. Then let's just assume our learning rate to be 0.1. Uh, can anybody tell me slope at y equal to x square? Hello. Okay. dy by dx equal to, for x square it will be 2x. Then at x equal to 5, slope will be 10, right? So x new will be 5 minus 0.1 into 10, which will be 4. So we got a new x, which is 4. So at x equal to 4, y is, at x equal to 4, y is 16. As you can see, our loss function has decreased. It was initially 25 and now it's 16. So we keep doing this until we find a minimum y. That is, if a y starts increasing again, it means that we have already found a minimum function. This is called gradient descent. So let's say at x equal to 4, we did this again, then x new will be 4 minus, learning rate is constant for a algorithm. So it will be 0.1 into slope at x equal to 4 is 8. So our new x is 3.2, right? And we'll keep doing this. So our x will keep coming here, and it won't directly come on 0. It might come this side, right? That's possible. Then we'll do it again. It will come here. This will keep happening until it comes on 0. That's how this method is called gradient descent, and that's how we find a minimum loss. We don't differentiate, double do that double derivative and all that j double stuff here. So I hope you understood what a gradient descent is. If you were not able to follow anything, you can just ask in chat. Then there's one more method or architecture or model. It's called logistic regression. So unlike linear regression, like linear regression was a straight line, so it can give any value, right? But logistic regression gives value between 0 to 1. And if you remember, I told you regression returns a numeric value, right? But even though this is called logistic regression, it's actually a method of classification. Uh, Now, if you look at this function, you can easily understand that it will give a value between 0 to 1, right? But let's just take that spam mail example again. One mail was spam and one was not spam. Let's say spam is 0 and not spam is 1. So logistic regression will return some value between 0 to 1. If it returns value greater than 0.5, then it will be called not spam mail, because not spam was 1 and spam was 0, right? So I hope you understood how this logistic regression works. This function is called sigmoid function, and its equation is 1 upon 1 plus e to the power minus x. Now you might be wondering what we put in this x, right? If you remember, we had a score function in linear regression, wx plus b. It will return some y value. That y value we put here, and we get some number between 0 to 1. And based on that, we classify. So let's see if you're still listening. Which of the following is classification task? Predicting house prices based on area, predicting whether stock price of a company will increase tomorrow, predicting nationality of a person, all of this. So would someone like to answer this question? Which of the following is a classification task? Hello? Do you need a poll for this question also? Just say a option. C. Ashwarya. Okay. Yeah, right. Predicting nationality of a person is a classification task. Rest all are regression tasks because all of them are going to return a numeric value. House price, whether stock price will increase tomorrow. B is also actually a classification task. Whether stock price of a company will increase tomorrow. The answer will be in yes or no. So it's actually a classification task. Okay, now let's move on. Uh, so now our next topic is unsupervised learning. If you remember, supervised learning had both labels and features, but unsupervised learning they only give us labels and not features. And then now obviously if we don't know labels we can't classify. Then it has different sets of problem. Like first just read definition. Unsupervised learning refers to the use of AI algorithm to identify patterns in datasets containing data points that are neither classified nor labeled. So just like they've told, our data set or information won't be classified or labeled. It won't have any labels. In unsupervised learning we make groups of similar data, which is called clustering. Then one way to cluster our data is called k nearest neighbors. So what we do in k nearest neighbors is, 1 minute. So okay, let's take a email example again, spam and not spam. Uh, you had a graph given or data given. Let's say this axis had features one. Like both axes have features only, right? Because we don't have labels here. And this was some feature two. We were given two features. Based on that, we were deciding if a mail is spam or not spam. Let's say blue dots are not spam and red dots are spam. Now we have been asked to find whether this black dot is spam or not spam. So what we do in k nearest neighbors is, like, we choose some random number k. Here I've chose 7. Okay. Then we make a small circle around it of some radius. You don't need to worry about radius. Let's say this, I made this one circle. Then it got 1 point inside it. That is a not spam point. NS is not spam and spam red and S is spam. So NS was 1. Then I increase the radius of my circle with a black dot at center. Now I got 3 more points. Now 2 was spam and 1 was not spam. So total spam points are 2 and not spam points are 2. Then then I increased the radius of my circle again. Now I got 3 more points again. And now my total is 4 spam points and 3 not spam points. As you can see, I've got 7 points and my K was 7. So I got 7 nearest neighbors. And according to those, 4 was spam and 3 were not spam. So my black dot is going to be spam, obviously, since more number of spam points are around it. Okay, so this is k nearest neighbors. But in real world, k won't be 7. It would be something very large, like 1 lakh or something. We will catch enough points to actually decide whether it's a spam or not spam. 7 is actually a very small number. So this was one method of clustering. Now that was unsupervised learning. Now let's move on to reinforcement learning. In reinforcement learning, we are given a data with neither features nor labels. We are just in an environment and there's a reinforcement agent. It's nothing, it's just AI, which perceives and interprets its environment and takes action and learn through trial and error. So what it's actually trying to say is, it takes decision based on its environment, then it gets some feedback from the environment whether its decision was right or wrong, and then it learns from those feedbacks, and then it learns to take better decisions. Like it learns itself. So I hope you understand this meme now. Supervised. They gave me so much to read and test. Unsupervised, me too, but at least they told you the answers. And reinforcement, at least y'all don't make your own books. Now, with these ML models, we face some issues. Few to mention are underfitting and overfitting. Like, underfitting is a scenario in data where a data model is unable to capture the relationship between the input and output variables accurately, generating a high error rate on both the training set and unseen data. So, what underfit is actually trying to say is, like, we train a model based on a data, right? If you remember. So our model, when it gives wrong answers to our training data, the data we feed it during training is called training data. So when a model give wrong answers to our training data, it's called underfitting. Then overfitting is a concept in data science which occurs when a statistical mode model fits exactly against its training data. When this happens, the algorithm unfortunately cannot perform accurately against unseen data, defeating its purpose. Uh, for overfitting, let's take an example. You made a model to detect whether it's a cat or a dog, right? uh, now say lo- Now let's say all dog images were taken outside in sun and all cat images were taken indoors. Now if you give a cat image which was taken outside, your model is going to say it's a dog because it has found a shortcut now. uh, since it learns from its past experiences of the data we feed, and all data was saying outdoor pictures are dog, it predicted the cat picture also as dog. So our model keeps trying to find a shortcut, and sometimes it overfits that it exactly fits on the training data, but it give wrong answer on our new unseen data or test data. I hope you understood what underfitting and overfitting is. So now we'll move on to our next topic, which is deep learning. But what's the difference between deep learning and machine learning? So the first step in understanding the difference between deep machine learning and deep learning is to recognize that deep learning is a machine learning. So yeah, deep learning is just a part of machine learning. Like you can see from definition, machine learning, an application of AI that includes algorithm that passes data, learn from the data, and then apply what they have learned to make informed decision. And deep learning is a subfield of machine learning that structures algorithm in layers to create an artificial neural network that can learn and make intelligent decision on its own. Uh, I believe you might have heard this term somewhere, neural network. It's in our brain. Our brain uses a neural network to take decisions. So in deep learning, there's also a new artificial neural network, which structure is exactly like a brain's neural network. But if DL is machine learning only, then why should we use it, right? While basic machine learning model do become progressively better at performing the specific function as they take in new data, they still need some human intervention. If an AI algorithm returns an accurate prediction, then an engineer has to step in and make adjustments. With a deep learning model, an algorithm can determine whether or not prediction is accurate through its own neural network. Like what this actually is trying to say is, let's say a model gave wrong answer, right? In machine learning, a human will have to step in and correct the mistake. But in deep learning, it's AI corrected based on its algorithm. No human help is required. Once you start the model, it will see its own mistake and keep running the data until it gets accurate answers. By the way, this is just one part of why DL is better than ML. It has many more reasons you can see on internet. So how does a deep learning works? DL system helps a computer model to filter the input data through the layers and predict and classify information. Deep learning process information same manner as human brain. It is used in technologies such as driverless cars. Okay. Now, so this is how a neural network looks. You might have seen such images before. Neural network are multi-layer networks of neurons that we use to classify things, make prediction, etc. But what are neurons? A neuron takes a group of weighted inputs. So a neuron takes some input, it applies a function on them, and then returns a output. Then that output is fed to another layer of neuron, and it does the same thing. until we receive a final output. A neuron takes a group of weighted inputs, applies an activation function, and returns an output. Inputs to a neuron can either be features from a training set or output from previous layers neuron, just like I said. Then, but what is this activation feature function? Activation function is used to determine the output of neural network, like yes or no. It maps the resulting value in between 0 to 1 or -1 to 1, etc., depending upon the function. On the right side, you have been given many activation functions: sigmoid, tanh, relu, leaky relu, max out, ilu. We'll see some of this today. So, relu, rectified linear unit activation function. The ReLU is the most used activation function in the world right now, since it's used in almost all the convolutional neural networks or deep learning. ReLU is half rectified from bottom, as you can see f of z is 0 when z is less than 0, fz is equal to z when z is above or equal to 0. So for positive features, it follows y equal to x equation, and for negative ones, it returns a 0. Its range is from 0 to infinity. Uh, I believe you guys know what functions are. You put in some value, you will get some value. Then, so activation function are nothing but just functions based on which our neurons are going to return some value. If you input some x, it will give some y. That's all. Then the sigmoid or logistic activation function. The main reason why we use sigmoid function is because it exists between 0 to 1. Therefore, it is especially used for models where we have to predict the probability as an output. Since probability of anything exists only between the range of 0 and 1, sigmoid is the right choice. Its equation is 1 upon 1 plus e to the power minus x or z, and at x equal to 0 it returns 0.5, as you can see in graph, or you can also try putting x here as 0. Now, what are epochs? A epoch in machine learning means one complete pass of training dataset through the algorithm. This epochs number is important hyperparameter for the algorithm. It specifies the number of epochs or complete passes of the entire training dataset passing through the training or learning process for algorithm. Epochs is nothing but like how many times we are going to pass the data through a model. Let's say epochs was 5. We'll pass the data 5 times through the model. That's all. So now I hope you have understood this basic theory of ML. We'll stop the theory part here. Uh, Now, obviously, ML has more theory and lots of things, but as long as tiny ML is concerned, we have read enough. We won't need anything else. So, but if you are interested in ML, you can go ahead and read on internet. There are tons of resources available. But the best thing to check whether you have understood something or not is to see if you understand memes related to it, right? So, we have some meme. The right one is my favorite actually. All your fans jump into the fire. Would you follow them? A machine learning algorithm. Yes. Uh, Thank you. If you guys did not understood anything, you can ask in chats. Now Mayur will take us through ML model. You might understand it there. So Mayur, you can take over now.
Yeah, okay. We'll have a 5 minute break.
Okay.
I'll start at 10.
Okay. Fine.
With this, you can stop sharing screen. Yeah, hello guys. I guess we can start. I have shared a collab link in WhatsApp as well as in chat. You can open that and you will code along with me in this collab notebook. Tell us in chat after you open this collab notebook. Yeah, are you able to edit that? Like write code in the box, the code blocks, code cells.
Yeah, Mayur, we can edit. We can write code in the cells.
Yeah, yeah, okay. So, having been discussed theory by Pratish, we'll now try to apply it to a real world data set. We'll build a neural network first of only one input layer and one output layer. After that, we'll increase it to we'll build with one hidden layer. So, what are machine learning model like this model? Not machine learning model. This is actually a artificial neural network. And what is the motto of this data set is to like if you will like enter uh, 28 by 28 pixel grid of like handwritten number, and your model should be like able to recognize which number it is. Like your if your handwritten number is 0, then it should predict that it is 0. And we'll see how we can increase accuracy, and we'll apply like most of the theory part whatever taught by Pratyush in this data set. So for this, first we need to import one machine learning library known as TensorFlow, and we'll use Keras to to run over top of this TensorFlow, because the functions of this TensorFlow are a bit difficult. So basically, Keras is like simplifying the functions in TensorFlow. Okay. So it is just a machine learning library which allows us to use the functions for machine learning and all. So we don't need to write manually the functions and all for that. So yeah, we'll start. You start. You also like code along with me. We'll import TensorFlow from TensorFlow Keras. From TensorFlow import Keras. Yeah, like are you following? Yeah, I hope you are following. Yeah, and then for plotting, we'll import matplotlib, matplotlib.pyplot, PLT, and to run it, we'll do percentage matplotlib inline. And, we'll also import numpy. Import numpy. Run this cell now. Yeah, okay. So we have imported all the relevant and the required libraries for building this building this artificial neural network. So the data set we will be, this is now the data set called MNIST data set, which stands for Modified National Institute of Standards Technology data set. Now this data set has 60,028 by 28 pixel grids, which have handwritten digits of handwritten digits, and each like corresponds to one label. Like the handwritten digit 0 will have one 0, like that. So it is like it is made by humans, and like we'll use this to train and test our model. Okay, we'll go into depth like what we are going to do like in training and testing. So first of all, you will import this data set into your variables called, will will split this data set into two, like x, not into two. We'll use one part of this, the 60,000 part of this data set as uh, to train our model, and the remaining and the other 10,000 we'll use to test our model. Okay, so just follow me. Like x underscore, will define x underscore train as the training input data, which we will be using to train our model, and the corresponding labels y underscore test, sorry, y underscore train only. And now we'll create another set which will be used for testing the model.
Mayur,
X underscore test. Yeah.
someone is saying voice is too low. Are you sure, Suresh, it's not your earphone?
Hello.
Because everyone else can hear him properly, I guess. Is anyone else facing same issue? Hello? Uh, you can continue, Mayur. I'll see
Yeah.
if anyone says anything.
Okay. Dot data set dot mnist dot load underscore data. Now, what this will do is this will store X train, the 28, the 60,028 by 28 grid image in this, and for training, we will be using this for training and corresponding labels y underscore train, and this is for testing. Okay, so based on like whatever we have like splitting into training and testing, we have features and label. Can you guess like what kind of learning is this? Like it is supervised, reinforced, or unsupervised? Any guesses? We are giving features and labels to our model. Yeah, right. It is a
Okay.
supervised learning. Yeah, what?
Nothing, sorry, continue.
Yeah. So yeah, you guessed it correct. It is supervised learning model, because we are giving our model the training data and the features, and all these are, you can refer this to as features and refer this to as labels corresponding to features. Okay, so now with this I'll uh, show you once the sizes and all of uh, size of these arrays and all. So size of blue, length of x underscore train, uh, length of x underscore test. Okay. Okay, I didn't find them correctly. Okay, so see, x underscore strain is of like 60,000 length, and this is of 10,000. Like there are 10,000 28 by 28 pixel grids in your test data set and 60,000 in your train data set. So, also I'll also show you the shape of training data set. That is, for shape you will do x underscore train dot shape. Tell again. See, it is a 3D array having 60,000 28 by 28 pixel 2D arrays. That is a 28 by 28 pixel image of grid of image. Okay. Similarly, you can check for test data. That is 10,000, 28, 28. Okay. Now, for better performance, we'll convert this into NumPy arrays. So x underscore train equal to np dot array train. I'll just copy this. We are just converting this to NumPy array for easy, yeah, for easy computation forward. Underscore this is okay. Yeah, next test file. Yeah, okay. We are now like done with completing this, converting this list into NumPy arrays. Now let's see one of the pixel. So let's say I do x underscore n of, let's say, 2. So this will print you one 28 by 28 pixel grid. You can see this. This has 784 elements, and this is how the digit looks like plt.mat show was covered yesterday. It was just like 255 is for brightest, so colors corresponding to this will be like the brightest, like this will be brightest yellow, and this will be like darkest purple. So plt.mat show will input this x underscore 10 of 2. C will be shift enter. See, so this matrix corresponds to 4. Okay, x underscore train of 2 corresponds to 4. Yeah, so this was just for illustration. Now we'll rescale this data, uh, this complete data, because now understand why we need to rescale this. Suppose your neuron is doing like your score has score function which calculates the weights, like linearly it calculates the weight, and it has an activation function of type sigmoid. Now sigmoid is a function which has y equal to 1 by 1 plus e power minus x. So if x is already too large, then like the difference between the y value, like the output values of the neuron will be like not much distinguishable. So suppose the number you want to detect is 4. So along with 4, the other neurons will also get activated. Activated in the sense they will also show like the similar range of numbers. Like suppose for the neuron corresponding to 4 is getting activated and showing output like some 0.25, and another is showing some 0.26, then you won't be able to distinguish like the number it is number we want to recognize is 4 or 5. So this is for like accuracy and to distinguish the output of the neurons. So I guess you won't understand, you didn't understand this. First of all, I'll tell you now the structure of what we are going to build. We are like what we are going to do is these 288 elements, this we will be using as input neurons. Okay, now this input neurons will be having 784 will have seven input layer will have 784 neurons which carry these numbers. Okay, suppose your output there will be 10 output neurons because the output will be determined like from 0 to 9, 0, 1, 2, 3. So there are 10 such neurons in output layer. Okay, so yeah, now what? Suppose your neuron takes input from these, those output neurons take input from this, and they use one simple weights which are like 784. Like it will have 784 weights and one bias, and it will give one big number if you use such numbers like 16 and 216 and all. And if you use your activation function like of type sigmoid, then this will be like very high number. So y will be like always near to 1. So in that case, your many of the neurons will get activated. Activated in the sense they will show like non-considerable difference between them, because of which we won't be able to recognize which neuron is like giving some extraordinary value. Okay, so for that we need to rescale this. So for rescaling, what we'll do is we'll just scale this to we'll map this 0, 255. The maximum of this is 255 and minimum is 0. So we'll map this to 0, 1. Now 0, 1, like this impacts a lot, because the thing is when your sigmoid function has the input variable x is smaller between 0 and 1, then like the function is like easily distinguishable. Okay, the difference between the output the outputs of neurons in output layer, like they are distinguishable if this x is like small. Okay, if this x is too large, then this exponential factor will already vanish away, and this will be like always close to 1. So we are rescaling it. So yeah, for rescaling, what we are going to do is we'll rescale x underscore x underscore train equal to x underscore train divided by 255. So that all elements are like now divided by 255, and also the test data set will also divide that by x underscore test equal to x underscore test whole divided by 255. Okay. Yeah. So we'll run this cell. Okay, and now I'll print the same 4. Print x underscore test of let's say train only, train of true to. See, like we have just rescaled this that 4, the pixels of 4 to this numbers like 0.94255. Okay, so this will like help us distinguishing between the outputs of the output neuron in our neural network. Okay, now the data like these arrays, these test and train sets, like they had 28 by 28 pixel. Now, because we are using 784 neurons in your input layer, we'll rescale this 28 by 28 pixel grid to a 1D array of 784 elements carrying the same. So we are just going to use the reshape function of numpy. So we'll do what? X underscore reshape to what we are going to do is 60,000 784. Similarly, we'll reshape Control C the training data set. Sorry, the testing data set. Reshape will be reshaping these two data sets. Now, what will happen with this is you will get 60,000. The number of data sets are like number of uh, grids are same, but the grids are now rescaled to 784. Okay, we'll see why did we reshape it again. So we'll run cell x underscore test dot reshape. Okay, okay, there are some 10,000. Yeah, there are 10,000. Okay, we cannot reshape. Okay, and also we'll store this in a variable called x underscore flattened x underscore train underscore flattened. Flattened equal. Okay, and just copy. Yes. Yeah, one equal to sign here. Yeah, see one of the flattened data set I'll show you. X underscore train underscore flattened of 0 of 2, let's say of 2. See, this is a 1D array. This was 2D array. This 2D array was like converted to 1D array with reshaping this data set. Yeah, okay. So yeah, are you guys like following till now? Yeah, any doubts till now? Are you following? Put yes in chat if you are like done till now. Yeah, please respond. Like, are you following? Now we're like going to important part of this. Yeah, okay. I'll move forward. Okay. So now we are like going to architect our or build our neural network model. Now, as said before, our neural network model has 784 input neurons, no hidden layer for now, and it has 10 output neurons, and based on the output of this 10 output neurons, we are going to determine the what the input was and what is the label corresponding to it. Okay, so what we are going to build is there are like two types of neural network models. They are one is called sequential and one is called functional. Now what sequential model is like, it is like stacking of layer over layer. Like the next layer will be dependent on the previous layer, and so on. Like it is like stacking. And functional model is like any layer depends on any other layer. Like the third layer can again depend on first layer for input, and let's say fifth layer may depend on fourth layer for input. That is sequential, and fifth layer may also depend on the input layer for input. Okay, so that is like a more complicated model than sequential. So sequential model is like just stacking one layer above another. Okay, so for here it is not any stacking because we are not using any hidden layer here. Okay, so we'll build a sequential model that is of type dense. Now, what do we mean by dense? Dense is like, are all 784 neurons will be associated with each output neurons. Like the each of the 10 output neurons in the output layer, they will be taking input from all the 784 neurons which carry the brightness of the pixels, this brightness of the pixels in the data. So we flattened this data for like to give input to each of the 784 neurons. So the 784th neuron will have input 0 and so on, like this. This will be input to the input neurons. And yeah, so we'll first build this. So for that we'll do model dot keras. Yeah, so we have started using keras over TensorFlow for building our model. So keras equal to, sorry, not keras equal to, sorry, model equal to keras dot sequential, keras dot sequential, and in this keras dot layers dot den. There will have 10 outputs. It will take input from 7 neurons. So we'll mention input underscore shape, that is 784 equal to, and yeah, what we have done till now is we have created one output layer. Okay, output layer which has 10 neurons. It is taking input from 784, and since it is of type dense, or each one of these 10 output neurons is connected with this, taking input from 784 input neurons, and we are using activation function of type sigmoid. So the activation function for the neuron, for the output neuron, is of type sigmoid. Okay, now we'll be using this now. As Pratyush described, our model gets trained like we get learn from as humans get learn from the mistakes they do. Same our model is going to do. So the way it will like learn from its mistake is like while it is compiling model.compile, we'll use a optimizer. I'll tell you what an optimizer is. Right, optimizer equal to Adam. We'll use Adam optimizer loss. This is the same loss function which was discussed in the theory. Sparse. We'll use this loss function sparse categorial underscore cross entropy. Now, like, don't get afraid of this entropy. This is just a activation. This is just a loss function, same as what you did in mean square error. Okay, we'll also do this with mean square error and take a look at our accuracy, like how well our model behaves, and we'll use metrics type accuracy in the accuracy of model. Okay, here also one comma. Yeah. Optimizer Adam. Yeah. Okay, so I'll explain you in short what an optimizer is. Now in gradient descent, you have like heard the term LR, that is the learning rate, and the way it is just like a algorithm which modifies the weight and the loss, like uh, way the what law learning rate and weights. It is just a one type of algorithm that modifies your weights and algorithms, weights and learning rates of gradient descent when you are this it is getting compiled when there are epochs in the when the data set is running epochs. So we'll see what epoch is. For now, optimizer does that thing, and we are specifying the loss function we are going to use for this is actually this all like learning from the loss function, like of drawing inferences from loss function and improving the model is like known as back propagation. Okay, this all is for back propagation. Which with this back propagation, like we'll know how our model, how well is our model behaving. Okay, now we are like now done with the structure of model. So it is using Adam optimizer. There are many optimizers, but we'll but we are using Adam optimizer here. Yeah, I'll run this cell. Keras dot Keras dot layers dot dense 10 comma input underscore shape. Okay, here I guess we didn't give call. Yeah, it compiled. Okay, now we are done with creating a model. Uh, now we'll be training this model. Now, like this has some random weights in it now. For now, now while training, it will adjust the weights as per our input, and first I'll write the statement for that. So that is model dot fit is basically for training. We'll give the input data set, that is flatten x underscore train underscore flattened. If you give tab, like it automatically completes that. Okay. And comma y underscore test. Sorry, is also train. Y underscore train, and we'll do this for 5 epochs. Now, what is an epoch? It is actually discussed before. I'll discuss that back. What this 5 epochs mean is your data will be compiled. Your data will be sent through the neural network for 5 times. Okay. So I'll first run this and it will take a bit time. Model.fit x underscore train underscore flatten underscore train and model.fit x underscore train underscore flatten and epoch. Yeah, let's refer this ones. Model.fit. But I'll copy paste. X underscore train underscore flatten. Wait, is there any problem in defining the libraries? Oh, yeah, here it is. I will compile this again. Still. Yeah, it is printing, but train to flatten. dot liquid. One underscore train underscore this one, sparse underscore category underscore cross into. Yeah, okay. I guess I defined the loss function with the wrong, like spelling errors in loss function, because it is like just accepting a string. Okay. Yeah. See, so you can see that with every epoch, the loss is like going on decreasing, like from 0.46 to 0.30 to 0.28 to 0.27 to 0.266. And you can also see that the accuracy is also going on increasing. Okay. Now let's the final like okay, so with each epochs, what it is doing is it is adjusting the weights. It is adjusting the weights, and since the loss is going on decreasing, the accuracy is also going on increasing. Okay. Now this model has like learned only the training data that you gave it. Okay. It is not like uh, tested itself on the testing data set. Okay. So we'll test it now. We'll take exam of your model using model.evaluate. Evaluate. In give input of x underscore test. Now I'm giving test to this test dataset flattened x underscore test underscore flattened comma y underscore test and y underscore test, and yeah, just I'll compile this. See, though, so the accuracy of our data set is like 92%. Is like showing on the scale of 1, and loss is this. Okay, so the thing is, if I change this function, this is like just PNC of different optimizers, different loss function. And now I'll change this to mean squared error. Add underscore error. Okay, and now I'll trim this. See, so the accuracy is so less, like just 11%. So it will like print 2 instead of 5, like it will print anything. See here, like the loss is like, see the accuracy, it is just 10%. So this defining a model is crucial, and this activation function, this optimizer, this loss, like they are what that determine the efficiency of your function. So we'll keep it category cross entropy as the loss functions, parse categorial cross entropy. I hope we don't get that problem again. Yeah, we got that. Categorical, okay, it is categorical. Okay. You can even train your model with 10 epochs. It will even better increase your accuracy. We run this again. Why is it showing so less accuracy? Oh, I'm using ReLU also. Yeah, it changes to sigma. Okay. Yeah, so you can change this. You have to just do P and C of this loss function optimizer and correct activation function to improve the efficiency of your model. Okay. It will train, it is training. Yeah, okay. See, you can see that accuracy is increasing. Now with the test data, yeah, after this it will print the accuracies. Yeah, okay. So we are now for now we are done with testing the model and determine the accuracy. So what our model from the test data, it can be inferred that our model is like determining for 92.4%, it is determining the number correctly. Okay, I'll now print one of the, I'll print now y predicted, y underscore predicted. I'll show you what the neurons in output layer give us as output. Y underscore predicted equal to model dot predict here we give x underscore test underscore flattened, x underscore test underscore flattened. Okay. And now I'll print y underscore predicted. Matrix with 10, I'll just print one of it. Let's say I print the fifth one, or let's say I print third one. Yeah, I'll print third one. Okay, so third one has some outputs outputs of this kind. Okay, this is 9.9 into 10 e power minus 1 and so on. Now, yeah, I'll show you the plot of this. Okay, plt dot mat show. Now I'll show you the x underscore test, not flatten. I'll show you x underscore test and test of obviously we predicted third. Okay, so I'll print third only. And see, so it was 0 and From this, it can be inferred that the one with the highest number is representing the representing the this representing this zero. Okay, so this neuron gave the maximum high value, and see others are like having low values. So our model is predicting based on this this activation of neuron. So this neuron got activated more in the sense it is outputting more numbers. Okay, it is outputting a greater number as compared to these all. Okay, now what does this neuron is? Okay, uh, instead of printing the array, I'll just show what the array was. Okay, so this is the zeroth element of the array. Okay, so yesterday we have done that argmin and argmax. So the index which has the maximum number is our predicted value. Okay, so why? So what we'll do is np dot argmin, np dot not argmin, np dot argmax, argmax of what y underscore predicted. For now, I'll do third one. Okay, so see, it has predicted it as 0. Okay, now I'll show you the accuracy and all of our data set. So what I'll do is y underscore. This I guess you can do it on your own. Yeah, I'll share this. This is like just same as what we did here. Okay, so here what I'll be doing is I'll be like, I'm just doing some math here. And do you want me to do this like it will print the same accuracy as this? What it was printed after this epoch? Sorry, after this. Okay. Do you want me to do that, or can I move forward? It is same math as what this function is doing. This function y model dot evaluate. It will show you the error and accuracy. I'm determining the accuracy using based on the data we got. So do you want you to do that, or you'll understand it on your own? I'll share this with you. Yeah, like you can respond. Can I continue with that, or I should explain that, or continue move forward? Yeah, hello.
Hello?
Yeah.
You can continue again.
Yeah, okay. I'll once show you that. No problem. So let's see like what were the predicted labels. So I'll do y underscore predicted tab underscore labels again. These are the labels which are of our training data set, like the test data set, which we predicted using our model. We store it in a numpy array to np dot rmax of I label for a in or predicted. Okay. When I run this, and if you want to print this, like this will show the labels corresponding to each of the data set you predicted. Like it will uh, print all this 10,000 predictions of like which is the maximum of all this 10 in this pair. See, like y underscore predicted has 10,000, is of size 10,000. In it, it has 10, uh, 10 numbers each. So we are just finding the index of this maximum number in each of 10. So the size of this will be also 10,000. Okay. And what I now will be, now what I am doing is I'll do deviation underscore array. This is deviation array. Just naming the array equal to what I'll do is np dot sort the absolute value. Like just calculate the absolute of the difference. So what I'll do is y underscore predicted labels, y underscore predicted underscore labels minus y underscore predicted, y underscore test, sorry, y underscore test. Okay. See how much that value is deviating. Okay. And I'll shift enter this. Okay. Now I'll print this deviation array. Okay. Okay, you can see that there are some zero indicates like the predicted and the test, like what we want, what actually they are same. Okay, and these numbers, there are some of this number, like there can also be 8, 9 in this array. The array is too big, is like it has 10,000 elements show, so it is showing us this much only. But you can see that our model is not 100% accurate because there are some deviations. You can see that something like here may be like the predicted label may be like 0 and the test label may be 9. So it is like writing the absolute here. Okay, so we can based on this we'll calculate the accuracy. So I'll define another matrix A equal to np dot count underscore non-zeros. Okay. Non-zero non-zero non-zero, and I'll pass the argument to this as deviation underscore array. What it will do is it will filter out, it will like uh, take all the uh, deviated elements from this array, like non-zero elements from this array. I'll print the length of this array, the length of A, and you can see that np dot count number. See, so 760 of 10,000 elements are like predicted wrongly by our model. Okay, so based on this, you can determine accuracy as 200, or we'll do it. Yeah, we'll do it on the scale of 100. 100 minus the percentage of the like 760 divided by 100, divided by 10,000 multiplied by again 100 divided accuracy. Sorry, this will not print accuracy. Print accuracy. And see, so accuracy is just 92.4%. Okay, so now we'll analyze a bit the data, the predicted data, and the predicted and actual data in test while testing the array with the help of confusion matrix. So we'll create what is confusion matrix is like. Yeah, I'll show you. Just like follow me. Tf dot math dot confusion and dot confusion underscore matrix and equals to y underscore test and predictions to y underscore test underscore y underscore predicted underscore labels. Sorry, predicted and now I'll print this. See, so this is the confusion matrix we got. I'll show you it in more a good way. So for this, we'll import one library known as import cborn and with this we'll plot this matrix plt dot figure. Don't go much into deep, like this is for illustration, just for illustration purpose. Figure size equal to 1,7 and what sn dot heat map m annotation that is, yeah, we want to annotate true and you want to describe is like if you do this b then it will show some binary number. I want a digit number, so I'll do it equal to d. Okay, and print x label lt dot x label. This cborn is just a library on top of numpy, so we are able to use this plt dot and all plt dot, sorry, on the top of matplotlib, not numpy. Plt dot x under x label predicted lt dot y underscore label y label that is actual. See, so we have printed confusion matrix. So this is, you can see that the from this all these elements in black colored are like they sum up to 760, and these are remaining 10,000 minus 760 elements. That is some 9,240. Okay, so you can see that when 0 times when the actual value was 1, it predicted 0. You can interpret like, suppose let's say we'll take this 2. What does this 2 signify is actually 2 times the value was 3, but our model predicted as 6. Okay, so that's how like we can analyze from our confusion matrix. Okay, so I'll build another model of with one hidden layer. Now, till now what we discussed is a model with no hidden layer. Now we'll see like how it impacts accuracy when you build it with one more hidden layer. For that, what we'll do is we'll copy this same. We are just stacking one more model to one more layer to this with Keras dot layers dot dense. Then what we'll do is 10 not will take 100 neurons in input layer. They will have input underscore shape equal to 784. Okay, 784. I'll give one comma also here. 784. Activation of type, let's say, let's give this temporary loop, and no longer the output layer is no longer associated with 784 neurons. It is associated with the 100 neurons. Okay, so it is 100 and okay. We'll give one comma here. Okay, so we have built one neural network which has one hidden layer. So this keras.layer.dense is like the hidden layer which takes inputs, which has 100 neurons, of which each neuron takes 784 inputs, and the activation is of type, it is using activation function as relu, and relu is like max of 0 comma x, like for x smaller than 0 it is 0, and for x greater than 0 it is y equal to x, and okay, and sigma is like you know that. Now when I same, I'll be doing same things now. Model dot sequential. Again, I'll predict with, I'll do some epochs. See, control C. Just copy paste that. See, the accuracy starts with 92%. Okay, so you can see like what using a hidden layer like impacts your model. Okay, so till training is, I'll do what? Do this model dot evaluate. Oh, sorry, model dot fit identity. Okay, we'll just copy paste this model dot evaluate. Oh, sorry, is it model dot fit here? Oh, sorry, you have to do evaluate here. Okay, still it gave output, but with this you will evaluate better. Model dot. Oh, I have to run all restart and run again. Okay, what we have done is like just introducing this new layer, nothing much. That is like impacting too much on accuracy. Like the accuracy of your model jumped from 92.4% to some 98.6, something, yeah, something 98.6%. So you can like estimate how using a dense layer like impacts your model. I guess model dot fit is only fine. Oh wait, we are what we sorry what I did is we are like testing it. I have to give you here test. Okay, two epochs here while evaluate. See this accuracy. Run this again. It is like not much difference. I'll change it this to 725. Okay. Yeah. I'll fix. I plotted this. This model. I trained this model with 5 epochs. Now I'll evaluate model dot evaluate. Test it with the training data. X underscore test underscore test underscore flattened. Underscore test. See, so our accuracy is like now 97.4%. And again, I'll plot for you the confusion matrix. Yeah, you can like do that model dot evaluate with what you'll do is I underscore predicted. Yeah, you can like basically plot. Yeah, you can do that as a task, like plot the confusion matrix for this and uh, see like you can analyze this. The plotting a confusion matrix, you will get very less numbers in this because this time the accuracy is 97.44% on your testing data set. Okay. Yeah, I hope most of the things were clear today, and I hope you enjoyed like how machine learning, how does a neural network work as this is same as the way you learned like walking, like you fell down very much many times and like you learn from that. In same way a neural network learns by analyzing the loss function it gets, and yeah, that's all. Okay, I hope you enjoyed the session. I'll send the recording and the Google Colab and the slides too. You can check that if you have, and again if you have any doubt you can ask in group. Okay, like are you having any doubt right now? Yeah, I can stop the session now. Yeah. Bye guys, thank you.